wants to view it down the road. Okay, so volume, we're talking about volume here. And we have our three different methods of calculating volume. I should say, in response to a question that was asked, I tend to group disk and washer together because they're essentially the same. There's the same theory and a very similar picture between the two of them. So it's worth mentioning when we can use one versus the other, but it's telling that I sort of lump them together, I think, that they're very, very similar. So our three methods of volume, we have volume by cross sections. I should write out the word cross section here so we don't get confused with the variable x. Cross-sectional volume. This is if we're trying to integrate our volume of our loaf of bread by slicing up it into slices of bread and integrating up the area of each of those slices. So this is if we have some shape, some amorphous blobby lump of bread going from x equals something to x equals something. And at any given x value, and I'm saying this with x, but it could also be with y. So at any given x value, you can take the cross-sectional slice, and the cross-sectional slice, maybe it's a circle or something like that. But every individual cross-sectional slice can be examined. It has some area. The area depends on the value x you were looking at, right? So if I looked at a different x value, if I looked over here, for example, at a different x value, I would get a different cross-sectional slice, which would itself have slightly different area. Maybe it's a bigger circle, right? So each of these depend on the specific area. This is like a of x2 drawn here in red. We have a of, maybe I call this x1 here in pink. But in general, each of these cross-sectional slices has an area. It depends on which x value we look at, so we can index it and create this function a of x. And then the actual integral, to compute the whole thing, the actual integral is going to be the integral from x equals a to x equals b of this area function a of x. Figuratively integrating the area of each slice of bread. You can think of these as slices of bread, integrating up the two-dimensional area of the slices to get the three-dimensional volume that we're looking at. These were the first kind of volumes that we looked at when we first began talking about volumes. And so it's easy to forget them in the midst of all the confusion about disks, washers, and cylindrical shells. But the sort of prototypical example of these would be to give you a shape, right? So there could be some shape in the XY plane. And I'm not going to go through a full example right now, although we're welcome to down the road later in this session. I just wanted to illustrate this. You're given some sort of shape in the XY plane, like maybe something that looks like this. And then you're often told that this is a base for a solid with cross-sectional slices that look like something, right? That look like a square, that look like a circle, that look like a slice of bread. And so the idea is that we have this three-dimensional volume, but this shape that I'm seeing is really its two-dimensional shadow, or as if I'm flying over it, like a bird's eye view of the shape. So this is its base, but you can imagine it coming out of the screen with cross-sectional slices that look like, squares or circles or something, kind of similar to the picture we had here. And so if you see that as your setup, you are probably dealing with a cross-sectional volume problem. Notice in particular, all of our other volume problems, these volumes of revolution, involved an axis of revolution. So it involved some axis upon which we revolved the image to create the picture. So if there's no axis of revolution, we're probably looking at one of these cross-sectional slice problems. And again, we can go through an explicit problem to practice that down the road. But yeah, at the moment, I just want to keep doing an overview of volume. So I'm going to pivot to the next kind of volume. Are there any questions about what we have written up here so far? What questions do you have? Seems okay? Okay, so let me go ahead then, and let's talk about the other kind of volumes. We have volume by not by cross section, we have volume of solids of revolution, and that can be either a disk / washer, which I'll break up into the two specific kinds. So I'll talk about disks and I'll talk about washers so we can notice their difference. And then the third one will be these cylindrical shells. So the setup in these kind of problems is always going to be the same. There's going to be some region or curve that we're revolving. So we're going to be given some region in space. I'm just going to draw something sort of silly here, something like this. And then we're also going to be given a volume of an axis of revolution. And the axis of revolution, at least in this class, will always be either perpendicular / parallel to the x-axis or parallel to the y-axis. So perpendicular to one or the other as well. So let's pretend, just for the sake of this picture, that my axis of revolution is parallel to the x-axis and perpendicular to the y-axis. I'm revolving around this axis right here. So what we end up doing is we have this region, and as we revolve it, we're going to get this this three-dimensional shape, this rotationally symmetric three-dimensional shape, and our goal is to calculate that shape's volume. So I often fail at these pictures, but let me see if I can draw a decent enough picture of what we have here. Right, so as we revolve, I'm going to take every point in this region and revolve it. This point ends up looking like this. This point sort of similarly looks like that. This point up here is going to revolve further, so it's going to look like this. And so what we end up with, this is one of my better ones perhaps. What we end up with is this sort of, I don't know what you would call that, some sort of like bracelet or armlet looking thing. It has this hole in the center, but in particular, all of this outer region, and here I'm probably gonna ruin the picture by drawing all over it, but all of this sort of outer region is completely shaded in, right? So it constitutes this three-dimensional volume. There's a tube in the middle. There's this hollow space in the middle, just based on how I've drawn this. But there's this outer region that we care about. So the main difference that I often talk about when I talk about disks versus washers is this question of, can I stick my arm through it? And I've drawn this fun, awkward picture a couple times in which I sort of, draw a little cartoon hand coming through here. So this is a thing with a hollow tube. It is something that you could stick your arm through. And if we can stick our arm through it, that means that we are dealing with a picture involving washers. If we cannot stick our arm through it, if there's nothing, if we cannot stick our arm through it, then it would be something involving disks. This is a slight bastardization of what's actually happening. Let me show you a quick example. I'll draw another picture. So I'm sort of lying to you when I say that. Because if I had a region that looked like this, if I had a region that looks like this, I'm going to revolve this region around this axis. Right, so still perpendicular to the y-axis, still parallel to the x-axis. If I were to revolve it around this, I'd end up with this kind of goofy looking shape in which sort of this opening over here, there's not an opening here, right? So it's sort of like a, it's like a little cylindrical piece, but this, cone shape has been carved out of it. So could I stick my hand through this? Up to a point. I can sort of get my hand up to here, but I cannot punch all the way through because, there's no opening here at the end. So I cannot technically stick my hand through this picture, but because there is this hollow region, I'm going to want to use the washer method again. So this is still a washer style problem. So what is the sort of washer formula versus the disk formula? And let me actually, just for the sake of completion, let me also draw a picture. Let me go ahead and draw a picture of something that just requires the disk method. If I have something that kind of looks like this, maybe my region looks like this. And if my axis of revolution lines up perfectly alongside here, then notice what I would get when I revolve is this sort of football looking shape. Right, and there's no, there's like no hole or hollowness whatsoever when I go to take a look at it. So this is an example of where we could use the disk method. So what is the disk method? What is the washer method? And what are their formulas? Well, it's secretly the exact same formula that we used above, right? It's still just a cross-sectional area. And what we're doing is we're integrating our weird, possibly hollow loaves of bread by integrating up the area of each of the slices. But the key observation we can make here is that if we take a slice that is perpendicular to the axis of revolution, right? So I'll make sort of an arbitrary slice here, yes, here, and here, just in the middle. What I get is always going to look like a circle or like an annulus, right? So let's take a look here. When I make the slice in this first picture, it's going to give me this sort of pink annular region, right? An annulus is just a one-dimensional donut, or a flat donut, I should say. So we're going to end up, if I pulled out that cross-sectional slice and I put it on its side and laid it flat, it would look like this. Similarly, here, I'm going to end up with this bigger circle and this smaller circle. And the annular region is going to be what I get when I pull that out. That would be an annular region. Here, there is no middle hole to pull out. There is no hollow region. So this is just a circle. And the name's disks and washers, right? A disk is just describing a circle, like a filled in circle. So this is our disk. While a washer, right? I mean, a washer, think of it as like one of those little hardware pieces, right? The thing that you put around the screw or the nail, or whatever, probably a screw. Not a hardware guy myself, but if we put the washer around the screw, we see that it sort of looks like this. It's flat and it has this hole in the middle. So this is a washer. But the point is that when it comes to disks and washers, we have well-defined area formulas because they're made up of circles. So here we have a given radius, capital R, and the disk has area. Yeah, pi r squared, pi times the radius squared. Well, for these kind of pictures over here, we have two radii, right? And then it's going to be the big circle, the area of the big circle, which we'll denote with a big R, minus the area of the little circle, which we'll denote with a smaller radius, little r. And so that just becomes area equals pi times the big R squared minus pi times the little r squared, and that would be the area. So in essence, what we're doing is using the same formula from above. We're just doing it in which the area is explicitly these areas of circles. Love it. So a question was asked earlier, how can we tell the difference between when we want to use the washer method, when we want to use the disk method? It really comes down to an understanding of the picture. sort of an idea of, does it have this hollow space? Do the cross-sectional slices look like full discs, or do they look like annuli with a hole cut out of the middle? Do they look like discs, or do they look like washers? And so what we've seen a lot in this particular sort of subsection of the class is that being able to understand what the picture looks like plays a really big role in how we analyze it and set up an appropriate integral. And we'll see that's exactly the case here. Now, this is all in contrast to washers. So in contrast to cylindrical shells. So we've noticed now that the discs and the washers are both just secretly the cross-sectional slices again, just where our cross-sectional slices are nice circles or annuli. The cylindrical shell method is something completely different. So cylindrical shells I'm going to draw kind of a similar picture to what we had on the previous page. Let's actually see if I can recreate it. I'm going to have something that looks like this. So this is our region. This is our axis of revolution. And so just like on the previous page, we are going to revolve this shaded area around this axis of revolution, and we are going to get a picture that kind of looks like this, right? That sort of weird flared out thing you can stick your arm through. So we'll get the exact same picture. On this previous one, notice we took a cross-sectional slice, which was drawn here in pink. We took a cross-sectional slice that was perpendicular to the axis of revolution. And what we did then was we traced out, let me make it even more explicit. We took sort of this, there we go. We took this line segment here, right, that was associated with this X value, this cross-sectional slice. We took that line segment and swept it out. This is equivalent to if we take sort of a stick like this, and we sweep it out to create a disc or a washer. What we're going to do now is take that same kind of stick, but turn it sideways and sweep it out like this. So what would have been a flat disc now becomes a shape with some sort of three-dimensional substance to it, becomes this cylinder. And we'll draw it as follows. And in essence, the big idea with cylinders is that instead of making our cut perpendicular to the axis of revolution, as we did before, we are instead going to make it parallel to the axis of revolution. So in this picture, we would choose a Y value. We would make our slice like this. And now this is the line segment that we would revolve around the axis of revolution. And that would give us a corresponding cylinder, right? We call them cylindrical shells because they're cylinders, but they're hollow cylinders. So it's just the surface area on the outside of the shell, like penne pasta or something like that. And this cylindrical shell, right? If I pull this out and I take a look at it, every cylindrical shell, every cylinder, I guess, has a few measurements associated with it, including the two most important ones. It has the radius of the cylinder, and it has the height of the cylinder. And the surface area of a cylinder is just going to be 2 pi times r times h, right? 2 pi times r gives us the diameter of the bottom, and the diameter of the bottom times the height is exactly the, I'm sorry, I said diameter, I meant circumference. 2 pi times r gives us the circumference of the bottom, and the circumference of the bottom times the height is giving us the total surface area. So what we ultimately want to do is we want to create an integral in which we're integrating 2 pi times r times h, where r and h are these functions, these variable functions that depend on the chosen value that we're looking at. And so the cylindrical shell volume, I'm gonna loosely say this. I'm gonna say volume looks like it's an integral from some value to some other value of 2 pi times r times h, and then it's either dx or dy, where r and h are functions. All right, cool. So yeah, here's where we begin to get into some of the complications, because now we've seen the exact same surface and we see that we can potentially integrate it in two different ways. I should say we have the same volume, and we can integrate this volume in two different ways, using cylindrical shells or using disc/washers. And the main difference in each of these is that one of them, we are creating little sectional slices that are perpendicular to the axis of revolution. So that was our disk example. Let me go back a slide. In our disk example, our sort of fundamental starting point was to make a little slice that was perpendicular to the axis of revolution. And that would give us this washer, and then we would integrate up all of these washers. When it comes to cylindrical shells, we're still making a cross-sectional slice. The cross-sectional slice, in this case, happens to be parallel to the axis of revolution. And as a result, we get a shell, and we're going to integrate up all of these different cylindrical shells. And because we had the same picture, we can notice that in the previous one, we are making our cross-sectional slices depend on the x value, right? This is just based on the picture itself. Here's our axis right here. We have this cross-sectional slice that depends on this x value, and different x values will correspond to different cross-sectional slices. While in this picture, we're making our cross-sectional slice depend on the y value. I shouldn't say cross-sectional slice, we're making our cylinder depend on the y value, and different y values will correspond to different cylinders in the picture. So this specific picture, this specific example, this would have to be an integral involving y. Everything depends on which y value we're currently looking at. So this would be an integral as y goes from some value to some other value, 2 pi times the radius function, which would be a function of y, times the height function, which would be a function of y, and we would be integrating dy. So the additional consideration in all of these problems, it's not just disk and or wash, or I should say disk/washer or shell. It's also disk integrating dx or dy, or shell integrating the other one, right? So one of them dx, the other one dy. The question is, which one do you want to use? All right, and that's a broad overview of these many different methods for calculating volume. I want to pause here and see what questions you have or what I can clarify. So Val asked a question, can there be instances where the integral depends on x? This is for the cylindrical shell method that we're looking at right now. Yes, the answer is yes. But let's take a look at what that would be like. And I think you'll quickly see the understanding here. Let me actually, Val, I'm going to momentarily minimize the chat just so that people in the class can see the entire screen. I'll reopen it in a second because I want to keep this picture up here, and I want to draw a related picture in which the cylindrical shells will depend on the x value. So I'm just going to go ahead and give away the punchline. The punchline is that our axis of revolution will be a vertical one. It'll look like this. Because in this case, if we have, let me draw my football example from before. Is that okay? Yeah, let me draw a rocket ship. Let's draw a rocket ship. That sounds fun. So if my original region is this region here, if my original region is this region here, and then I revolve it, I'm going to get this rocket ship looking shape coming up like this. This could be completed, and I'll draw on this in two instances. This could be integrated, this volume, using the disk method if I wanted to integrate dy. So I would pick a y value. Every y value has a little, piece that gets revolved, and that piece of revolution would correspond to a given disk. And the disk would have a certain area. It would be given by pi r squared, but it would depend on the specific y value that I had. So this would be the disk method integrated with respect to y. Or there we go. Or I can choose a specific x value, like this, and create this line, which, when revolved, creates this cylindrical shell right here. Right? And when I pull out that cylindrical shell, it's going to look like this. And it's going to have a certain height and a certain radius. And both of those will depend on the specific x value that I chose. So r of x, h of x. And then my integral in this case would be the integral as x goes from something to something of 2 pi times r of x times h of x dx. So in essence, figuring out which one is integrating dx and which one is integrating dy depends entirely on whether our axis of revolution is parallel to the x-axis or parallel to the y-axis. And that's sort of the trick here. That's the trick for this sort of problem. Yeah.
So in the case of cylindrical shells are like opposite from disks and washers, like they're when cylindrical shells would depend on y, disks and washers would depend on x.
Yes, that's correct. The question, Val, was about whether or not disks and washers are always opposite. So if one of them would always depend on dx, then the other one would always depend on dy. And the answer is yes. Yes. Based on the axis of revolution, you can decide whether you want to make your slices perpendicular to the axis of revolution or parallel to the axis of revolution. And that will influence not only whether that's dx or dy that you're integrating over, but also whether the shape you get when you revolve is a flat disk/washer or a sort of three-dimensional looking cylinder. Yes, 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 yes. Yeah, these are great questions, everybody. I appreciate them. Any other questions that we have here? Chat, there we go.
Another question for me.
Yeah, for sure.
When we do integrate with y, the a and b values are going to be y values, right, and not x values?
Yes, that's right. That's right. So the question was, when we integrate with respect to y, the a and b values should be y values, not x values. Yes, that's correct. In fact, let's do, I'm trying to keep an eye on the time. You all have been asking a lot of volume questions, which is great. I think volume is one of the thorniest topics that we've talked about. Let's do an explicit example in which we have to integrate dy, just to sort of see, or in which we might prefer to integrate dy, just to see what happens. And then with time we have left, we can either do more examples with volume, or we can pivot to another topic, depending on what you all are interested in. But let's come up with an example. I'm just gonna try to make something up. And fingers crossed I can come up with something that's kind of interesting. So let's see. Okay, I'm not as quick on my feet as I want to be. Let's say that we have a region that is governed by the equation. Whoops. region between y equals square root of x. Don't know why I gave myself so much room. Region governed by y equals the square root of x plus 2. Y equals the negative square root of x plus 2. And the line x equals 1. And we'll figure out where we want to revolve this around in just a second. I'm going to leave that blank for now, but revolve around the following axis of revolution. So these functions, right, the square root of x kind of looks like this. The negative square root of x kind of looks like this. And because these are that function plus 2, it means they start at 0, 2. So we're going to be looking, here's one of them, looks like this. Here's the other one, looks like this, right? So this was the first function, y equals root x plus 2. This is negative root x plus 2. And then we have this line x equals 1, which remember, when we say x equals 1, that is a vertical line. That is specifically this vertical line corresponding to the x equals 1 value. So I said our region is the region bounded by these curves. When we draw out all of these curves, we see that this is really the region that we're talking about. And let's go ahead and revolve this around. Well, I guess it doesn't really matter. Let's go ahead and revolve this around the line. I can do this. Let's revolve it around the line y equals 3. So this was, again, 1, 2, here's 3. And so our axis of revolution is going to be this line right here. And so what we end up with, if we think about it, as we revolve, we'll end up, here, this is going to be an example of a bad picture, I suspect. We'll end up getting what kind of looks like a sideways bundt cake pan, right? Sort of a bundt cake or one of those sort of ring cakes. You'll know what I'm talking about. So we end up with something that kind of looks like this, right? Oof, and I'm probably going to erase some of those extra lines because I think that muddies the picture a little bit, but I just want to point out that you could stick your hand partway through, but you couldn't stick it all the way through because you can't push through that final barrier. So let me make sure, does this picture make sense? The idea makes sense more or less. Okay. So let me erase some of this stuff just so we can keep our picture clean. I will point out that there are 2 ways that we could integrate this. There are always going to be 2 ways, right? We can either try to integrate it with respect to dx or integrate it with respect to dy. And depending on which way we choose, we'll either be using disks or washers. So let's actually, I tried to come up with one on the fly where we had to integrate it one way versus the other. I don't think I actually achieved that, but I think we can integrate this both ways. So let's set up both integrals and see how we can do this. The first, right, the one that we're all a little more comfortable with is just to integrate with respect to x. So that would mean taking an x slice not to muddy my original picture, so I'm sort of drawing it like this. Right, but this would involve taking a slice at a given x value, taking this piece and revolving it around that axis of revolution. And notice, because this is perpendicular to the axis of revolution, this is going to give us a disk / a washer in this case. Right, we're going to get this washer as a result. So we can go ahead and we can pull out the washer and take a look at it. Right? Washers have a big radius and a little radius. And the big radius in this case is going to be going from the line itself all the way down to this lower function. Right? So that big radius is drawn here in green. It's all the way from the axis of revolution down to the lower function. So the big R in this case, again, it depends on x, but it's going to be from the height of 3 down to the height of negative root x plus 2. So it's 3 minus negative root x plus 2. Which we can rewrite, that just becomes 1 plus the square root of x. Simplifies. The other radius, which I'll draw in orange, is going to be from the axis of revolution down to this upper function, right? It's going to be that smaller radius right there. And so that's going to be little r of x is going to be 3 minus, and then it's going to be positive root x plus 2. And so that is going to become 3 minus root x. I'm sorry, 1 minus root x. And then when the dust settles, so we can just set up the integral. We won't actually compute the integral. We'll sort of stop once we've set it up. But notice this is being integrated as x goes from 0, the leftmost x value, up to x equals 1, the rightmost x value. And so this ends up becoming the integral as x goes from 0 to 1. We have our pi times that original function squared minus pi times the second function squared. And we're integrating with respect to x. And at that point, we would be done. Okay, so that was setting up this integral using the disk/washer method and using x variables to integrate. Let's see if we could do the same thing using y variables. And based on Carter's question from before, we know that if we're going to switch the variable, we're also going to switch the method. So this will become a cylindrical shell method. But let's make sure that we can see that. We got our two functions. All right, we have our region that we're integrating. And then we have our axis of revolution given right here. All right, so this time we are going to take a y value, and at a given y value, interesting. We are going to take a y value, and at a given y value, we are going to construct this cylindrical shell right here. Sorry, I don't know why I chose to do that one. I'm going to do this one. I'll make a smaller cylindrical shell that will be easier for me to draw. It's still not pretty. So we get that cylindrical shell up there. If we pull out the cylinder, I often set them upright, and I apologize if that actually makes things more confusing. I hope it doesn't, but notice I'm sort of turning it 90 degrees when I set it upright like this. I end up getting my cylindrical shell that looks like this. I know that the formula will be 2 pi times r times h, and the question is, what are each of those values? They will depend on y. So let's start with R. The R, right, that's the radius of the cylinder. That's the distance from the axis of revolution down to the Y value in question. That's that distance right there. And what we end up getting, in this case, right, we had the axis of revolution was at a height of 3. And so this ends up becoming 3 minus Y. I said R of X, that should say R of Y equals 3 minus Y. At the same time, we have our H, and let's take a look here. The H, the height of the cylinder, right? Again, turned it sideways, so it's a little confusing. The height of the cylinder is actually supposed to be this distance right here. And so we have to figure out what that will be as a function of Y. All right, and so what we'll see, right? What we'll see, we have at the moment as a function of, I guess we need it as a function of Y. The distance will literally be the distance from this curve up to this curve right here. This curve is X equals 1, and this curve is X equals question mark, right? So it's a difference of these X values. The upper one, quote unquote, the upper one slash the rightmost one is equal to X equals 1. The other one is X equals question mark. And at the moment, it's written as Y equals, I guess I'll just use my black pen here. This becomes, at the moment, this is Y equals root X plus 2 or Y equals negative root X plus 2. But what I really want to do is transform that into a function for X. I want to end up with an X equals, and we can do this by subtracting the 2 to the other side. So either plus or minus root X equals Y minus 2. And then we can square both sides. So we end up getting the function X equals Y minus 2 quantity squared. And indeed, we realize that this is the function X equals Y minus 2 squared. It is a parabola opening sideways, and it's been shifted up 2 units, which is, 2 units in the positive Y direction. So this is a parabola, but because it's sideways, we're sort of flipping the role of X and Y. And so we end up being able to see that in this case, X equals Y minus 2 squared. And finally, we are in a position where we can calculate our integral. And like before, we'll just focus on setting it up. We won't actually calculate it all the way through. So it's going to be an integral from some bound of integration to the other, but these are going to be Y values. And we'll look at that in just a second. This is going to be 2 pi times the radius function, 3 minus Y, times the height function, Y minus 2 squared. Finally, for the bounds of integration, we want to go from our lowermost Y value, which will be this one here at Y equals 1, up to our highest Y value, which is here at Y equals 3. And we're good to go. We have done it. So what I'm going to claim, right, and you all can verify this if you're interested, what I'm going to claim is that these two integrals, which look relatively different from each other, will actually give us the exact same answer. And that answer is the true volume of this bundt cake looking solid region that we've created here. One of them using discs / washers and the other using cylindrical shells. Man, I love this stuff. That's just so cool. Any questions, comments, concerns about anything that we have up here right now?
Is the height not 1 minus y minus 2 squared? Because of your x equals 1.
Oh, what did I say? What did I say?
You said the height was y minus 2 squared. Right?
Yeah, no, you're totally correct. I am so sorry. Yeah. No, that's a great question. So the question was, it was a point of clarification, and I'm definitely wrong here. So I'm glad that this was clarified. The height function, right? So this is this orange, which I'm now tracing over in red. The height function was this distance. And so it should be the distance from x equals 1 to x equals y minus 2 squared. So that means that it shouldn't be this. And let me actually erase that. What it should be the height should be 1 minus y minus 2 squared. Yeah, that will give us this distance here. I think what I was calculating was the distance up to the function. What we really want is the distance from the line x equals 1 down to the function, and that's given by this. So yeah, that's a great point. Okay, now if you calculate those, they should give us the same answers. Okay, so we don't actually have that much time left. We have about 5 minutes. So I'm happy to try to answer any final questions that you all have, though we won't be able to get into a topic quite as meatily as we did here with volume. That being said, though, I said it before, I'll say it again. I think volume is some of the thorniest stuff that we've looked at over the last couple of weeks, especially because there are so many options in how we go about approaching a volume problem. So sort of thinking about some of those nuances, drawing these pictures and thinking about how we might want to calculate the volume is a really valuable skill. I think drawing and thinking through that process is almost more valuable than the explicit remembering of the formula and everything, though of course you will also have to do that. Any final questions about this or any other topic? Okay, well, hey, listen, if there aren't any questions at the moment, I think we can go ahead and call it 5 minutes early. I'll stop the recording, but I'll say just a few quick reminders about today and the weekend and all of that. This is more mundane stuff. This isn't test related. So those of you in the recording, you're not missing anything. I'll see you later.